Wait, what is the rule for dividing when we're working in mod? It is this. You can divide by d in mod m as long as d and m don't have any common factors. This is saying that if you have congruence between two numbers in mod m, you can divide both sides by d and preserve that congruence as long as there's no common factors between these two. Why is this? Let's look at some examples first. Here we are in mod 8. Let's look at 30 congruent to 6 in mod 8. Here's our 30, and we can see that yes, it is 2 less than 32, which would be in the 0 spot. So in the 6 spot, and what happens if we divide both sides by 2? Does it preserve congruence? Well, we get 30 divided by 2 is 15. 15 is 1 less than 16, so it's in the 7 spot. That is not the same as the 3 spot. It does not preserve congruence. What about, same example, 30 congruent to 6 in mod 8, and we'll divide both sides by 3 instead. Does it preserve congruence? Well, we get 30 divided by 3 is 10. 10 is 2 more than 8. 1, 2. It is in the 2 spot. It worked. Let's take a look at mod 9 this time and look at 24 congruent to 6 in mod 9. Here it is. And what happens if we divide both sides by 2? We get 24 divided by 2 is 12. 12 is 3 more than 9, which is in this spot. 1, 2, 3. And yes, it does match. It is in that 3 spot. 24 congruent to 6 in mod 9 again. Divide 3 on both sides, and we end up with 8 congruent to 2. Is 8 congruent to 2? Definitely not. 8 is over here, and 2 is over here. That's not the same spot. So we do see that 8 and 2 having a common factor doesn't work, doesn't preserve congruence. 8 and 3 not having a common factor does work. 9 and 2 not having a common factor does work, and 9 and 3 having a common factor does not work. So let's look a little bit more closely at what's happening here. When we're in mod, what we're doing is we're going around and around and around as many times as we want, and always ending up back at this spot to then finally travel the last little distance. We can think of this as if we're laying out the number line. So we're going around and around and around, and we end up finally in the same spot where we started, just to travel that last little distance to end up in a spot of whichever congruence class it matches. So let's look at mod 8 again, and let's look at dividing by 3. So here's that same example, 30 congruent to 6. When we divide it by 3, it ends up in the same spot as 6 divided by 3, both congruent to 2. So that worked. And let's look a little bit more closely at what's happening. This section right here we can think of as being somewhat extraneous. So as many multiples of 8 as we can, we'll just section that off and say that 30 is equal to 24 plus 6, and then divide both of these by 3. We end up with 24 divided by 3 being a multiple of 8. So this part goes to a 0 spot, and then we just add on the 2. So we end up going from 30 divided by 3 to 2, 0 plus 2. Now let's look at dividing by 6, and we'll stay in mod 8. So same origination spot, 30 is congruent to 6, and we'll divide it by 6, ending up with 5 from 30, and ending up with 1 from 6. So that didn't work. And let's look a little bit more closely at why. So when we split the 30 into 24 plus 6, this 24 divided by 6 does not end up in a 0 spot. So the final result of 30 divided by 6 is this 4 plus the 6 divided by 6, 1, ending up at 5. So here's all of that just rehashed again, and we can see clearly at the bottom here that when the divisor and the mod number have a common factor, then that common factor divides away the mod so that this section is no longer a multiple of the mod. In general, here is the proof. We'll get the whole thing on the page. Continued on the next page. And here we get our result. Suppose that m and d do not have a common factor, then we get the result that congruence is preserved when we divide both sides by d. This is exactly what we wanted, but it is only one case. So, as a bonus, let's look at case number 2. Here we go. Case number 2. Suppose that m and d have a common factor. Well, surprisingly, it does turn out that occasionally congruence is still preserved when you divide both sides by d. And here is an example of that. So it's not guaranteed if there is a common factor, but it is guaranteed if there is no common factor. In my last video, my proof of my Klintberg conjecture, I misphrased some things. When dividing in mod, here is what I should have said. Because p does not divide 2 and 2 does not divide p and 2 have no common factors. So we can divide both sides by 2. And then down here, it is very important that p is prime in this case. It only works if p is prime. Because p is prime, p doesn't have any common factors with any of its congruence classes. 1, 2, 3, all the way up to p minus 1. So we can divide both sides by all of these. So in order for my Klintberg conjecture to work, it does hinge on the fact that p is prime. I was just so excited about this part that I breezed over these sections, but they are very important. So thank you for keeping me on track. I'll see you next week.